This is Jason McIntosh with McIntosh Applied Engineering. In this video, I'm going to discuss how you can use impedance and sensitivity lookup tables to model the behavior of a microphone. I'm going to create a modeler module here. I'm going to just going to pick a microphone. The behavior of this microphone is almost entirely determined by the acoustical loading impedance seen looking into the microphone and a transfer function from the pressure at the front of the microphone to the voltage out of the microphone. So these two functions, the acoustic impedance and the sensitivity, largely describe the behavior of these microphones, particularly omni microphones. Some vendors are happy to give this information out in lieu of internal SPICE models of these microphones. And so if you are able to get this data from those vendors, this video will show you how you can use them. I don't have this data, so I'm going to use Aries to develop a data set from this Sonian microphone that I just created. So again, I need the input impedance and the sensitivity curve. To get that, I'm going to use a pressure source to excite the microphone. I then want to look at the voltage out. And this microphone requires a DC supply, so I'm going to connect a DC voltage up as well. And the default voltage of 1 volts DC is sufficient to power this microphone. So I'm going to go ahead and actually, before I solve it, I'm going to want to excite this microphone with 1 Pascal source. So I'm going to change this to pascals, and I'll change it to a single Pascal excitation. So I'm going to go ahead and solve this now. I'm going to use the graph element, and first I will get the sensitivity curve. So I'm going to connect the graph element up to the microphone. So when I did that, this graph was generated. Now by default, the frequency analysis range is from 100 Hertz to 10 kilohertz. If you're getting lookup data like this from a microphone vendor, it's best to have this extended as far as you possibly can. At the very least, it should probably go from 20 Hertz to 20 kilohertz. I'll extend the solution range in Aries to cover that. So here we have the frequency response of that microphone. This sensitivity curve is in dB volts for 1 pascals. I'll go ahead and capture that to put. So I'm going to create a text file that has this data in it in space delimited format. I right-click on the graph, and I can get that data format for this curve by selecting to copy the current buffer into the clipboard. Now this, I'm not holding the control key down, so this is going to be in this is going to be in column format, not MATLAB format. So I'll go ahead and select it. I will go ahead and run Excel here. And I'll paste that data into Excel so I can have easy access to it. So here's the sensitivity response in dB. That can be used, but if you so dB is useful if you're only looking at the overall frequency response of your system. If the phase is important, the phase delay through the microphone is important, then you want more than just the magnitude of the response. You want the real and imaginary parts of the response. Phase is important typically for active noise control systems and so forth, or if you have a DSP system that's very sensitive to phase, you might want to capture it there. So to get phase out of this, I'm going to go to graph element, go to advanced options, and have it also plot real and imaginary. While I'm doing this, I think I'm going to have it set the line type to be a little heavier to make it easier to see. So if I go back to my graph, the lower curve now shows the real and imaginary part of the sensitivity response. I'm going to copy this into the clipboard as well. This time I'm going to use the second option to copy all of the traces. I'll go back to Excel, right click, paste, and now I get a column for each trace in the graph, but I really just want a column, one frequency, a real column and an imaginary column. So I'm going to delete these other columns so I can put that together. So this data now is in linear, real, and imaginary parts of the sensitivity of this microphone. This would hopefully be the data that you're going to get from the microphone vendor. Next, we need the input impedance into the microphone. To get that, I'm going to connect to the input terminal here, the acoustic port, and I'm going to plot impedance. Now when I go to the graph, I see the impedance in dB and the impedance in its real and imaginary terms. For impedance, you always need the real and imaginary parts of the impedance, whether it's behaving like a compliance or has a mass effect or it has a resistive effect. All that's very important to the behavior. Excuse me, to the behavior of the microphone. So I'm going to right click on this. Again, I'm going to copy all the traces into the clipboard. I'll go back to Excel and I'll paste it in over here. Same thing as before. I've got two frequency columns. I just want one frequency column and the real and imaginary part together. So I will go ahead and delete them. So here's my impedance data. Here's my sensitivity data. So this would be typically what you get from the vendor. To use these, I'm going to use three discrete Aries elements to simulate the microphone using those lookup tables. The first one is going to be a resistance term. This is going to be used to simulate the impedance seen into the microphone. To use this, we're going to load impedance data from a file. So I've got to create that file first. I'm going to go through and copy this impedance data to the clipboard. I'm going to run Notepad, paste the data in, and I'm going to save this to a text file, save as. I've done this before, so there's already a z.txt file. I'm going to double click and overwrite that. So that z.txt file contains this data now. I can go to this element, and one of its options is to load impedance data from a file. If I click on that, the z.txt file pops up. So I'll click on it, and it automatically recognizes that it has three columns, and it loads it into this element, and it'll be used as a lookup table. For information on how these elements work, you can right-click on them and select Help, and this describes how it works. It describes the file format for the text file, so forth and so on. This is the exact text that's in the manual. You can also bring the manual up if you go to the Help menu and select Model or Module. It'll bring up the manual for the modeler, and you can read about everything there. Okay, now this was imported, and it's going to be used as a series impedance. To make this look like an input impedance, I need to create a pressure release or a pressure ground element. I'll connect that to this side. I want to excite this, so I'm going to use another pressure source to excite it. So let's go ahead and duplicate it. And I'm going to come up here, and I'm going to copy this impedance data into buffer A, plot it. I'll label it mic. That actually came from the mic element. I'll come down here and I will look at impedance. I've got to solve this circuit first. And one thing I didn't do is I loaded the data in, but in order to use it, you need to select this check mark. Now the simple scalar resistance value has been grayed out, so that's no longer describing the impedance. The impedance is being described by that lookup table. So I'll go ahead and solve it, go back to the graph, bring the graph up, and now buffer A is in green. That's what we got off of the, oh, it's not labeled. Label disappeared. That's what we got off the mic circuit. So buffer, the green lines are from the mic circuit. The current buffer is in blue, and it's exactly underneath the the green lines. We might be able to see that if we zoom in or something. Nope, they are just exactly on top of each other. So we've successfully captured the impedance into this microphone in this resistance element. We now want to capture the sensitivity response. To do that, we're going to use an acoustical transfer function. This element I'm going to connect it to the pressure in the front, and I want this element to simulate the transfer function from this pressure point to this pressure point here. This element allows you can load data from a file if you want, but you can also paste it in from the clipboard. So I'm going to go ahead and go back to my Excel file, and I'm going to copy the complex data in. Right click, copy, and I'm going to go to this element, and instead of loading it from a file, I'm simply going to press paste. Aries looks at the data in the clipboard, and it's identified 3 columns, and it's asking you for what the format is for those 3 columns. The first one that's available is frequency, real and imaginary. These are in acoustical ohm units, and that's what we want to use. So I'm going to go ahead and click OK. So this element now has the sensitivity curve of this microphone in it. To see that, I'm going to go up here and plot. I'm going to copy the voltage response into buffer A, and I'm going to come down and I'm going to plot the pressure response here. Let's bring up the graph. Let's solve it. Calculate. Okay. Something isn't quite right. Let me figure out what this is. Okay. The problem is I'm still plotting impedance here, so I need to switch this to pressure. Now let's go back. All right. I'm going to get rid of the real and imaginary momentarily. So go to advanced options. We'll just plot magnitude. So you can see here that buffer A contains the voltage response from the Sonian mic. Buffer B is out of our acoustical transfer function. The shape of the curves are identical, but they're offset by 94 dB. Now this is because the mic buffer here, the green line, contains voltage, and the current buffer contains pressure. Aries automatically converts pressure to SPL, and it will plot all of the graphs using the label from the first curve that's being plotted. So this is actually dB volts, but it's not. But the label here is expressed in pascals because that's the SPL because that's the first curve. So we really would like to plot the output of that transfer function in voltage instead of having it converted to SPL for us. Now there isn't a simple Aries element presently to convert pascals to volts, and you can't mix elements. You can't connect an acoustical port to an electrical port. So we need to have a way to converting this pressure to voltage. Well, a simple classic omni microphone will do the trick. I need to create a ground element for it, and I'll hook it up. I'll move the graph to the omni microphone, hit calculate, and they're a little closer, but they're not on top of each other because this microphone has a default sensitivity of minus 42 dB. So I'm going to change this to a sensitivity of just 1 volt per Pascal, and now recalculate. And the two curves are right on top of each other. So we've now, basically, we've successfully simulated this microphone using the acoustical input impedance and the complex transfer function information using these three discrete elements together. Now, one thing about you have to be careful with this Omni microphone is that it is modeled using internal volume and a port. You want to make sure that the Helmholtz resonance of this structure isn't coloring your transfer function. So you can set the voltage, you can set the volume to be very small, set the port to be very large. So the Helmholtz resonance is going to be shifted way up in frequency. But we've already seen that that doesn't really make a difference. But you do want to make sure that you're basically getting a flat, absolutely flat response out of this microphone. Now, one thing I do have to point out here is if I go ahead and I turn phase on, so I plot the phase of what we got out of the microphone in green and what we're getting out of our three discrete elements in blue, the phase is different by 180 degrees. And the reason for that is this microphone, it's an artifact of how the math is done internally, but this is actually inverting the voltage here. So we need to put a negative sign in front of the sensitivity to correct for that 180 degrees phase shift. So if I recalculate now, both the magnitude and the phase from this microphone and this circuit are identical. So now we've completely captured the behavior of this microphone with these three elements. So again, if you get this type of lookup table data from the microphone vendors, that's how you can use it to simulate their microphone. This is the sensitivity. The units here are volts per Pascal, the real and imaginary part. Again, that's critical for phase information. This is the impedance, and the units here are acoustical ohms or pascals over volume velocity. And it's always critical to have the real and imaginary part for the impedance. If you have any questions about how to do that, please contact us at support@maellc.com. We're happy to help you. I hope you found this interesting, and thank you for your time.